In terms of the basic methodology, I suppose it's almost offensive to cover that in this group, but one thing to comment on is that in the setup where you have two groups and two time periods, and then you have a control group that isn't subject to the intervention in either time period, and then the treatment group is subject to the intervention in the second time period. This, of course, can be set up in a regression framework as in equation 1. It, of course, has a long history in the analysis of variance, right? This used to be called ANOVA, I suppose, before we called it difference in differences. And so because it's just basically looking at linear combinations of means, in this case among 4 groups. So, of course, the notation differs a lot, but one way to think about it is just in equation 1 without specifying y is being drawn from any particular group, but just letting dummy variables pick out the right means in effect. So if you label the two groups A and B, where A is the control and B is the treatment, and the two time periods 1 and 2, where the treatment happens in the second time period, then, of course, the coefficient of interest is delta 1 on the interaction term. So, of course, the way to estimate this is by ordinary least squares, or equivalently just compute the means and form the difference in differences as in equation 2. Okay, so I'm going to come back to this briefly. This is one of those cases where I was talking about the Donald and Lang approach to inference, where their estimate in this case would be exactly what's in equation 2, but we wouldn't be able to do inference because, again, there are 0 degrees of freedom according to that setup. Okay, so in order to do inference, basically we have to have more control or more treatment groups than we have parameters to estimate. But in this framework, of course, this is just like the comparison of means case. Often we do have fairly large sample sizes in each group, and so you can estimate these means reasonably precisely. That doesn't mean we can always get a very precise estimate of the treatment effect. I'll do a simple example later on. Now, of course, in the simple analysis, the assumption is that the paths would have been the same in the treatment and control groups in the absence of intervention. And of course, that might not be true. So what became popular was the so-called difference in differences methodology, where, and I've actually seen, I think, 4 differences used, where you actually get yet a different control group, and an example is laid out here, where you may be looking at some sort of change in policy at the state level. Say it's some health policy change that's supposed to affect people over 65. So you look at a state where the change happened and where a state that the change didn't happen, and then you choose as a control group younger people in both states. But then you're assuming that there wouldn't have been any difference in how the health of the treatment and there wouldn't have been difference in the paths in the absence of the intervention. So to allow somewhat more flexibility, you could you could choose. I'm sorry, I messed that up. There's one state initially, and then you have the young group and the old group both before and after. And the point is, there could be reasons why you see changes in the health of the older group relative to the younger group that have nothing to do with the intervention. And of course, one way to get at that is then to use a nearby state or something like that, and use the older population from that state as an additional control. And so, if you write the equation out as in equation 3, you get the dummy variables for the state, the group, which is E stands for elderly, second time period, and then when you put in all the interactions, the coefficient that you're interested in is delta 3, the so-called difference in differences estimate. So you can see what happens is for the elderly in the state with the policy implemented, that's the change in means here. Okay. Then this is the difference with the elderly in the other state, and then this is the difference for the young or the non-elderly in the treatment state. And so this is the estimated effect in the DDD case. Now, of course, you can add covariates to this, and that's why this formulation is especially useful, because all you have to do is add covariates to it and then go ahead. And, of course, the estimate won't be in this form, but nevertheless you interpret it as the same way. And the idea is that if there are compositional changes, you can at least control for that to some extent by adding covariates to allow for that. Okay, so inference in this case is, again, it's standard if we assume that all of the estimation, all the uncertainty comes through the estimation error in basically computing all of these means. Okay, this, of course, that object is simple to use as long as we assume we have large sample sizes and are going to treat that as being approximately normal. Okay. Now, before we go on to considering the multiple groups and multiple time periods case, there's this issue that came up with the last talk, and that is how we should how should we view uncertainty in these sorts of settings. The standard approach is, again, the analysis of variance approach, where the uncertainty comes through the estimation error in the means of each group. So a lot of these examples do have lots of individuals per group, and that's where the uncertainty comes in. The Donald and Lang approach that I talked about last talk is one example of where extra uncertainty is basically inserted into the problem. And you can certainly make a case for that, especially if you're thinking of the treatment and control groups being drawn from a bigger population of possible treatment and control groups. That's certainly one way to think about how there's this extra uncertainty due to this group effect. Okay, now, you know, in some sense, these are philosophical issues. What is the right way to think about how your sample is being obtained? Does it make sense to just condition on, the state that has the policy change and then choose a state that's next to it? Or should you think about the uncertainty being, well, what if you had chosen a different state as the control group, or what if you had chosen 5 different states as a control group? At the end, I'll talk about this work by Abadi, Diamond, and Hainmuller, where they basically allow for that kind of uncertainty. In fact, that's the focus of their work, is uncertainty really about how you choose the set of control groups when you're looking at these sorts of aggregate policy changes. So the Donald and Lang approach is certainly one way to introduce uncertainty, and in fact, for the most part, as we saw, the uncertainty is assumed to actually swamp the sampling error that you get from estimating the individual means, because we saw in the case that we called the small g case and use this Donald and Lang method, the way to apply that, you have to use a classical linear regression model, and so you basically have to assume that the estimation error can be ignored, where you're, or at least the variation at the individual level. Okay, so as I said, that one way to think about the uncertainty is that it should reflect the uncertainty about the quality of the control groups in the analysis, and I'll come back to that at the very end. But in the case, like I said, in the case of the standard difference in differences setup, if we really just have two groups and two time periods we don't have any degrees of freedom to work with. And, there's this question of whether we should just say we can't learn anything in this case, or whether there's enough uncertainty there to say, there really is a lot of enough uncertainty just in the estimation of the parameters to treat this as a classical problem in statistics and to do the inference accordingly. So just as one example of this, there's this application by Meyer, Viscusi, and Durbin looking at the effects of benefit generosity on the length of time on a worker spends on workers' compensation. It's the classic difference in differences setup. So in the main analysis, they use the state of Kentucky. They have information on duration on worker compensation both before and after the policy change, and the policy change is to increase the generosity of the benefits by raising the cap on earnings that are covered. So if you are a high-earning person, then the difference before and after the policy change is after the policy change, more of your earnings are covered by, or for, in this case, more earnings were covered if you are on workers' compensation. And of course, if you're a low earner, then the increase in this cap should have no effect on you. And so what they do is they just use the treatment group as the high earners, and then the control group is the low earners. And when they use, so they use the data on Kentucky, which is 5,626 observations in total. They estimate a large they estimate a large effect of 19%. So actually, I forget offhand what the increase in the cap was. Of course, whether this is a big number depends on that. But this turns out to be a big economic effect, so that workers are on workers' comp 19% longer than they would have been without the policy change. And the T statistic is 2.76. So it's certainly statistically significant, but it's not, overwhelmingly significant. If you do the same analysis with the state of Michigan data that they have, which is a smaller data set, 1,524, you get essentially the same point estimate, but you get a much smaller T statistic. And so in this case, this is not statistically significant. So in this case, it seems a little hard to argue that somehow there's not enough uncertainty here and that we should really impose more uncertainty on ourselves, especially if it means basically saying we can get this estimate, but we can't put any kind of confidence interval around it because we don't have enough degrees of freedom. So I guess that's the question, is in these sorts of examples, should we conclude that we really don't have any way to do inference in these particular cases where you wouldn't claim this is a really small sample size, yet there certainly is plenty of uncertainty in the estimate, which means that having more data on the within each particular control treatment group pair certainly helps with our inference. Okay. But if we have many groups and many time periods, then it makes much more sense to actually allow for other sources of uncertainty through group time level effects. So that's what I'm going to turn to next, this setup down here, where now there are 3 time subscripts. So this recognizes that the data are often come at the individual level within a state or group over time. Okay? And one way to write this model then is as in equation 5, where it's a fairly general model. There are time effects, there are group effects, there are variables that change with group and time, and then there are these individual specific effects. So these are the policy variables. So compared with what we did before, there are now 2 subscripts instead of 1, and now the data I represents the individual, G represents the group or state often, and T is the time period. And then there's this effect which varies at the group time level, and then there's the idiosyncratic component, and the idea is we have M sub GT individuals per group. So I already said that, full set of time effects and so on. So as in the cluster sample case, we can write this as an individual specific level model where the intercepts differ across G and T. And then we can think of the intercepts then being determined by that other part of the equation that just has quantities that vary by T or G or both. So it's useful to break this down because if we have a lot of individual observations per group time pair, then we can estimate these deltas in a first stage and then essentially ignore the estimation error in them, and then analyze this equation in a second stage, which then becomes a standard panel data analysis at a more aggregate level. Okay. Now, sometimes these things are not allowed to vary across group and time in an unrestricted way, so that the way this would be estimated then is there would be dummy variables for every group time pair, and then maybe some of these are allowed to vary or not. But the point is, if we assume that we have a large sample size within each group time pair, then really it doesn't matter how we estimate these intercepts, because we're going to ignore the estimation error in the second stage. Now, I should say I'm going to talk about some work, again, by Chris Hansen, where he does actually consider the case where you can account for the estimation error in this, but that's, of course, much more complicated, and so in practice, if this is going to swamp the estimation error, then it's going to be the most important thing anyway, and he clearly focuses on the case where we act as if we can analyze this equation. Okay, so once we do that, once we say we're just going to estimate this by ordinary least squares, putting in a full set of dummy variables for group and time, then we, as I said, are back to the panel data case. Now, an important contribution of the Bertrand et al. Paper was to show that if you just take this equation down here, this is a standard panel data model, then, of course, if you assume that there's no serial correlation in this error term, and there really is, then the inference is usually off, and it can be off by quite a large amount. So this notion of clustering in this case is clustering to account for serial correlation in these errors that are at the aggregate level. By the way, this, again, there's an asymmetry here in that we assume independence in the group dimension, and then the question is, how do you deal with correlation in the time dimension? Okay, it's tough to allow for correlation in the group dimension in addition to this. So these quantities here are independent across G, but possibly correlated across time. Okay, so now how can we analyze this in light of the cluster sampling stuff that we talked about? Let's see. I already talked about this. So this is how this is being handled, doing OLS in the first stage. By the way, one of the, as Hansen points out, this setup can be studied using a result by Amemia with this sort of structure on doing a full GLS. So if you start with this model here, and let's suppose that this is actually homoscedastic across all I, G, and T, and then we add this structure on the intercept and we do a full GLS analysis. Well, in fact, that's the same thing as doing GLS in two separate stages. So, I mean, in some ways, if you wanted to analyze the full problem, that would come down to analyzing GLS in the second stage, and the only issue is if you're going to account for the estimation uncertainty in the first stage. Okay, and so I'm going to proceed here as if we're ignoring that. Okay. Okay, so as I said, so we're going to proceed as if these things are large enough to ignore. Now, so here's the equation down here that you actually estimate in practice. You get the estimates of these intercepts, and then these are the policy variables that it may just be a dummy variable that takes on the value 0 for all states for some states in every time period, and then is turned on for some of the states in later time periods. But at this level, these could be anything, provided there aren't too many of them. And one thing we can do is apply the results of Hansen that I mentioned before. And one key here is that it does make sense to include a full set of time effects and group effects. And so if we're going to apply Hansen's results, allowing this to be serially correlated, then we really do need a large G, large T type framework in order for the inference based on the cluster robust standard errors to be valid. The only restriction really then, other than that G and T are both reasonably large, is that the serial correlation in this error term here has to be of a weakly dependent kind. That is, it can't have unit roots in it. It has to have correlation that dies out, as you get farther and farther apart in time. So this really just takes us back to the cluster sampling case, except applied to panel data, where we have a full set of time effects, group effects, and then what's left over here is not persistent. It's dying out over time. Okay, so that's why in the simulations in the Bertrand et al. Work, and then in Hansen's theory and simulations, basically show that these robust cluster methods work pretty well, even if there's a fair amount of serial correlation in the error terms. But there can't be really strong serial correlation, or it breaks down. Okay. Now, Hansen's follow-up paper to this was to point out that, well, yes, you can just do cluster robust inference in this setting, and the simulations show certainly, of course, G equals 50 is a focal point because of the 50 states in the U.S., and then they use various numbers of time periods to show that even as the number of time periods approaches 30 or 40, that it still does reasonably well. But if you really think there's some sort of parametric serial correlation here, then we should be able to do better in terms of inference by using some sort of GLS procedure. Okay, so the question is, what would be a good model for this? And certainly autoregressive models come to mind. In fact, even an AR1 model has got to be better than assuming, or at least ignoring, the serial correlation in the estimation of the coefficients of interest, which are the betas. So there are two issues here. One is, suppose you take the case where you have a reasonably large G, say 50, and you don't have a very, very large number of time periods, let's say 10, or maybe even fewer than that, but let's just say 10. And suppose you want to model this as an AR1 process. Well, as it turns out, the standard thing you would do, which is to estimate the equation by fixed effects, that is, time effects, group effects, and then estimate the betas as well, of course, in a first stage, and then get these residuals, and then just use these residuals in a standard autoregression to estimate a rho, to get rho hat, and then to do the standard GLS transformation. As it turns out, the rho hat isn't very well behaved in terms of estimating rho. In the case where this is a problem that goes back at least to the mid-'80s, noting that there's this bias in estimating an autoregressive coefficient in the case where you have a large number of cross-sections and a small number of time series. And in fact, even if the VGTs are actually serially uncorrelated, but you use the so-called fixed effects residuals to try to estimate that correlation, it's on the order of 1 over the number of time periods. So even though the underlying errors are serially uncorrelated, essentially it's that within transformation that induces serial correlation in them. And so you can imagine, of course, if the true process is an AR1, then using the fixed effects residuals with a small number of time periods is not going to produce a good estimate of the autoregressive coefficient. So what that means is that you can try to do GLS, but you'll be using a bad estimate of rho in the AR1 case, and generally you're going to use a poor estimate of it in the general in more general autoregressive cases. So one thing that can be done, of course, is you could say, well, I'm still going to do this. I know I'm not getting a very good estimate necessarily of the autoregressive coefficient, but I'll use it to do a GLS, or what some people might call a quasi-feasible GLS, in the sense that you're really doing the transformation without a good estimate of the variance-covariance matrix. And then the way to handle that is to then make the inference robust. That is a valid thing to do because essentially, if you think about this in the context of Hansen's previous work, the rho hat is not estimating the right thing, but it is estimating something. And so as G gets large enough, you can basically just treat this as a GLS problem with the wrong estimate of the variance matrix. And so as I mentioned before with random effects, there's no reason after you've estimated random effects that you necessarily have to take the variance matrix seriously. You can do robust inference. The same thing is true for an autoregressive model, right? You can do this in a pure time series case too, is say, well, I'm going to do an autoregressive transformation, but then not take that seriously in doing inference because maybe it was an AR2 or an ARMA 1.1 or something that I'm not really accounting for. So that is certainly a sensible thing to do, but Hansen's work shows that is inefficient relative to something else you can do. It's not surprising it's inefficient because you're doing GLS with the wrong variance matrix. And so what he does is he actually comes up with some ways to adjust the bias in the estimate of rho. And I'm not going to try to show those formulas, but the idea is that you can actually figure out up to a certain order what the bias in rho hat is, and then do an adjustment to get a less biased estimate, and then use that in GLS estimation. And he has, there's some nice theoretical results here. In the case where doing the simple thing should work reasonably well, that is when t gets large, because as t gets large, the bias from doing this particular thing and just ignoring any adjustment, it should work well because, again, the bias is going away. He has an iterative method which goes back and forth between estimating parameters and autoregressive coefficients and then doing the bias adjustment. It has the same asymptotic distribution as doing the simple thing, and moreover, it actually has the same asymptotic distribution when G gets large and T is fixed as the infeasible estimator, which would require knowing what rho is. So in the case when G and T are both getting large, it doesn't lose anything relative to the more standard method. In the case when G is getting large and T is fixed, it's actually the same up to first-order asymptotics as doing the infeasible GLS. And of course, doing the usual thing is not the same as doing infeasible GLS because with T small, that coefficient, the rho hat, is actually biased. There are some more theoretical things that you're invited to go read, such as the fact that you can show that if you look beyond the standard square root of the sample size asymptotics, then his method actually has some attractive features. So the question is then, if you have this kind of setup where G is reasonably large, T may or may not be large, you could just do the usual cluster stuff, cluster robust stuff, or you could apply this recent work by Hansen and try to do something that's more efficient. And his simulations do show that there are non-trivial efficiency gains to be had in these the standard cases where you have 50 states and 10, 20 time periods, something like that. Now, of course, there is a catch, right? You don't get something for nothing usually when you're doing GLS, especially when a time component is involved. And as in any case where you're doing a GLS correction that is accounting for serial correlation, you have to impose more on the regressors. And the restriction that is needed is that they have to be strictly exogenous now. Okay, so this means in a time series setting, as we were talking about in the more traditional panel data setting, that there can't be any kind of feedback between the errors at time t and these x's in future time periods. Of course, if you just do pooled OLS and use cluster robust inference, you don't have to worry about the strict exogeneity assumption. So the source of the efficiency gain does come at the expense of the stronger assumption on these explanatory variables, which, since this was called difference in differences, we're typically thinking that these are things that are measures of policy changes. So as a practical matter, if we have a setup where we have some states where there wasn't a policy and some states where there never was a policy acting as a control group, and then another set where there's no policy, a policy is implemented, and then it's there forever, then the strict exogeneity assumption is palatable because you don't get this idea that the policy is being changed based on what's happening in the past. On the other hand, if these are x's where they can be manipulated, and they are manipulated, then you would worry about seeing policy changes in future values of these because those might be related to what's happened to the output, the outcomes in the past. But this is just, the usual story. And what's always difficult in these situations is if you've done pooled OLS and you've done this feasible GLS, whether you've done the bias correction or not, and you get different answers in a practical sense, then do you attribute that to, that OLS was really inefficient and that, its confidence interval is very wide? Or do you attribute it to some failure like strict exogeneity? And that's always a tough thing to make. But one thing that's a tough call to make it, one thing that's true is you can't just immediately assume that something's wrong with the pooled OLS analysis, right? Because in some sense, it's the more robust procedure in that it delivers consistent estimators under less restrictive assumptions. Okay, but that's again always pretty much the case when we're dealing with time series data and doing serial correlation adjustments. Okay, now one other possibility that was studied by Kiefer some time ago and then has been looked at by Hausman and Kirsteiner more recently is, instead of worrying about making very specific assumptions about the serial correlation in the errors, is to use an unrestricted variance matrix. And in the standard panel data setup, this is the same as dropping one time period and then doing GLS on the remaining time periods, where you allow the variance matrix to be unrestricted. So this is attractive because you don't have to make an AR1 assumption or anything like that. But it does, and it works reasonably well if you don't have too many time periods. But since this matrix, which would be, well, in the case of t equals 10, really becomes a 9 by 9 matrix, by the time you get up to t equals 20, it's a 19 by 19 matrix that once you drop the one time period. And so it gets difficult to estimate that many parameters with just 50 cross-sectional observations. So there are some size distortions from doing that as the number of time periods grows. Of course, one way to account for the estimation error in the first stage is to, well, not do the estimation in the first stage, but basically put in the averages of the individual specific variables. Of course, that changes the time series properties of that error term now, because if you really account for the fact that this is there. But, in principle, you could do the same sort of, you could do a GLS analysis. It's also true, though, that this is weakly dependent, so you can just do the usual fully robust cluster sample analysis. Okay, let me just talk briefly about individual level panel data. I'll talk about this in a more sophisticated way in just a minute, but of course, if you start with individual level panel data and just have two time periods, then this is a very common model where you explicitly have unobserved heterogeneity and then you have the binary treatment. And this is, of course, once you difference away the unobserved heterogeneity and do least squares on what's left, if this is the case where there's treatment in the second period for some units but not treatment in the first period, then you just wind up with this equation here. So this is just the usual. This is a difference in difference estimate, but it's based on panel data where, of course, we're looking at the average change for the same units over the two time periods and then differencing those as the estimated treatment effect. So there are other things, of course, to do. We talked about these a little bit. If you have lots of time periods, it might make sense to allow for a so-called random trend or random growth if y is in logs. And then the way you estimate this equation, we talked about this. It depends on what you think about the serial correlation properties here in the unobserved, in the idiosyncratic error. So after you difference, you can difference again to remove this, or you can use something like fixed effects. Now this is, so if you write down a model like this these days, I think you're considered to be a little old-fashioned because you're just writing down, a panel data model, and without any counterfactuals or anything like that. But it's fairly straightforward to set this up in a counterfactual framework. So, if you start with this as the counterfactual outcome without treatment, and then yt1 is the counterfactual outcome with treatment. And the question is, how would you sensibly define an unconfoundedness assumption in the context of panel data? Well, this is one way where you allow for heterogeneities that would affect, the outcomes in the two different states differently. And then the key assumption would be that once you condition on that heterogeneity, which is unobserved, then treatment this is the full time series of treatment outcomes, is not related to the counterfactual outcome, whether it's in the untreated state or the treated state. So, not surprisingly, if you set up the problem like that, then if you work it through, and let's say you assume that, you assume linearity here where you allow for an additive time effect and then this unobserved heterogeneity, then you get, models like this down here. So where now yt, this is the observed outcome. So there are time effects, there's an individual effect, and then there's the treatment effect, which may or may not be changing over time. So that's under this assumption that says the difference in, I guess that's not, that's under the assumption that there's no heterogeneity in the treatment effect. Okay, at least none that depend, there's no unobserved heterogeneity. If you allow that, then you wind up with a model like this. Again, the equations are simple to work out. It's done in the notes. But the thing that's interesting about this is if you allow the treatment effect to be individual specific, then you wind up with this random coefficient model, which, we talked a little bit about before. This is a full case where you would have an interaction with the observed things, but then you also have an interaction between the heterogeneity and the treatment. And then the question is, what can you do about this? Well, in this case, if you're really sold on the notion that the only heterogeneity is on the treatment variable itself, then there are a bunch of things you can do. One that turns out to work is that you can actually just treat consider the case where we don't have them changing over time, but we allow them to change across individuals. Then we can just, treat them as parameters to estimate for each individual. Of course, that turns out not to be a good estimate of the treatment effect for each individual, but the average of them is a consistent estimate of the so-called average treatment effect. So, that's certainly one way to go, and of course there are formulas for getting the right standard errors of these things, or you can do it by bootstrapping the panel data outcomes. So as I said, that's a quick look at how the old-fashioned panel data stuff can be viewed from a more modern perspective if you choose to do that. And you can allow pretty much full heterogeneity in the treatment effect doing that. Okay, now back to more modern stuff. There are semi-parametric and non-parametric approaches to treatment effect problems as well. And one setting looked at by Athey and Imben, so we'll go back now to the case where there are two groups and two time periods, and I'm using their notation as much as possible. So the two time periods are 0 and 1, and the two groups are 0 and 1, with no treatment in the first time period, and so the treatment happens for group 1 in time period 1. Okay. And then we have these two, the counterfactual outcomes without treatment and the counterfactual outcome with treatment. And what they do is they basically relax the linearity assumption that is implied by the usual treatment effect model. And the way they do that is they think of the time period, they just index this with an eye observation. So in other words, you can think of just drawing from this population of people, and a time period comes with each individual unit as well as group membership. And then the assumption is that the counterfactual outcome is this function of the time period and then this unobserved heterogeneity. Okay, and so there has to be some restriction on this function here, and the function is that the restriction is that it's strictly increasing in its argument for each possible time period. Okay, now one thing that is not in here is group membership. So the idea is that the outcome of an individual for a given level, okay, will be the same in a given time period, this level, regardless of group membership. Okay, so that's a restriction. And then the distribution of the heterogeneity is allowed to vary across groups, but it doesn't vary over time within groups. So that's a stability assumption on the population. So you can express the standard model in this way. So that's the sense in which this is an extension of the standard model, because, of course, this has U appearing additively and then time appearing additively as well. There are no interactive effects or anything like that. Clearly, this is monotonically increasing in U, okay, and satisfies the other assumptions. So the usual, continuing with the usual linear model, can be expressed like this, where this error term V is independent not just of the group assignment, but also the time period. Okay, now you don't have to have full independence here because of the linearity assumption, so that would work. And then, of course, you get back to this kind of equation 31, which is just a different way of writing the standard difference in differences model, okay, where now the TIs and the GIs pick out the time period in the group. So what happens is that under the Athey and Imbens assumptions, you can actually recover the full distribution of the counterfactual outcome without treatment, conditional on being in the treatment group. Okay. Now, of course, if I put 1 here, that's identified from the data because we know the outcome in the treatment case for the treatment group. Okay, so I'm running out of time here, but the interesting result is, well, there are several interesting results, but is that this distribution function can be recovered from things we can estimate with the data. These are all distribution functions. This is for F10 is the CDF for group 1 in time period 0. This is group 0 in time period 0. This is group 0 in time period 1. And all of those things are estimable given data, and so you can actually estimate this, the CDF of the counterfactual without treatment under the assumption of treatment. Okay. Let me just mention one other thing that you can do with panel data, because it relates to what Guido talked about yesterday in terms of inverse weighting to estimate treatment effects, and that is this work by Abadi, and he considers both the case where you don't have panel data, but also it's a little more straightforward to actually see what happens when there is panel data. And he focuses on the average treatment effect for the treated, where, so this is conditional on having received treatment. This is the outcome under treatment. This is the outcome without treatment. That's the 1 and the 0. And you can also take away this conditioning if you want the average treatment effect itself. And what's interesting is that it actually turns out not to be terribly surprising, but the average treatment effect in this case can be written as a function of the observed data and the propensity score, as in equation 39. Now, the way this differs from the formulas that Hito talked about is that this is a change here. So this is a difference in the outcome over the two time periods, as opposed to just in a cross-sectional context where you have the outcome itself. So this allows essentially for heterogeneity that gets differenced away. Yet there could be some other source of confoundedness in the treatment assignment. So this becomes something that is easily estimated, or fairly easily estimated, because this is, again, we observe this for each unit. We observe the treatment status, and we can estimate the propensity score, and this becomes one of the inverse probability-weighted estimates, in this case for the average treatment effect on the treated. Now, and like I said, this is a formula that follows from earlier work. It's just derived now in a panel data context. Of course, instead of just using this estimator, regression adjustment can also be used in addition to this. Or if you look at the work by Heckman, Ichimura, Smith, and Todd, you can just use regression adjustment if you want. A regression version that pretty much said you should never use would be to do this. So the main reason I'm writing this down is to compare this with something that, this is at least preferred to something that you sometimes see. Here, this would be, so we're regressing the change in the outcome on treatment, the propensity score. Typically, this should be interacted with, if you want at least a more flexible specification, where this rho hat is the fraction, it's just the sample average of WI, and then you look at this coefficient for the average treatment effect. So this, of course, imposes some sort of strange functional form assumptions, but it's clearly preferred to doing this, which is a regression where you use the level of Y, because this isn't even as flexible as just doing the simple fixed effects analysis for this problem, which is to use differences. So because you're just putting in a propensity score here, and this thing doesn't change over time, so this propensity score is just estimated conditional on some covariates. And so if you are just adding something that doesn't change over time, that's less general than just putting in a fixed effect and differencing it away. So what's happening really here is that there's a differencing that goes on followed by a propensity score adjustment, okay? And that allows for more heterogeneity. And of course, if you have panel data, then you should be able to handle more heterogeneity, and that's what Abadi's approach does. Okay, so I guess I will have to stop there and then take questions. Yeah. Uh-huh.
And so what my question is, suppose you have a policy, you turn it on, okay, you leave it on. So the treatment, once it starts, stays on for some people. And the question is are there any formal results on measuring treatment effects correctly? If you have like long differences in differences versus short differences in differences? Did anybody tackle that? Or is that too tough?
Is Guido here to answer that question? Is there any work on long differences versus short differences? Yeah, right. Would you please repeat it and direct it toward it? maybe it's something we should take up afterwards because, yeah, I'm sorry. I wish I had an answer for you.